Hi, this is Rouhe, recording in Finland. I work at Aalto University, and I will talk about SpeechBrain at the code level. So I will answer what is the scaffolding that allows you to go on your command line and actually just type in Python experiment.py hyperparameter.yaml and get that to actually run a full speech experiment, for example, a full ASR system with SpeechBrain. In this first section, I'll just install SpeechBrain. So this is going to include some live code we're running inside a Google Colab notebook. And first, let's talk about sort of a software engineering perspective. So is SpeechBrain a library or a framework, or what is it? This is a distinction where, so libraries are something that you call yourself, and you kind of put together the program flow, and library might offer certain sort of functionality, like NumPy, for example, is a library that offers maths functionality, for example, the fast Fourier transform implementation here. And then a framework is something that calls your code. So the framework kind of has a prepared structure of how the program runs, and you just provide some key building blocks that kind of determine what the program actually does. So, for example, Flask is a web framework where you just write, for example, a couple of functions that define certain routings for your web server. And then you run Flask and you can access those routes. So SpeechBrain has actually a bit of both of these styles. So most of, sort of in terms of lines of code, most of SpeechBrain is just sort of neural speech processing building blocks and some utilities in library fashion, where you just call them in wherever you need them. But then SpeechBrain has the brain class, which has a predefined training loop, and you provide these certain methods, compute forward and compute objectives, and with those implemented, then the brain class can actually run this predefined flow of the training loop for you, which sort of then you don't need to write the training loop yourself. Saves a bit of effort. So since it kind of uses since SpeechBrain uses a mix of both sort of design patterns, then we wanted to call it a toolkit rather than a library or framework, since toolkit doesn't sort of have a really clear definition here. It's sort of a more loose definition. Then I also want to talk about the kinds of things that SpeechBrain is built upon. So first of all, PyTorch and the PyTorch ecosystem. PyTorch, of course, provides like the main computational muscle, allows you to run stuff on the GPUs, while even just the basic ability of automatic differentiation. That's all PyTorch, but besides all that, PyTorch also has a large ecosystem of things that already kind of use PyTorch or kind of implement something with PyTorch. For example, some researcher may have released the code for their new model, and that could use PyTorch. So then the point is, we want SpeechBrain to be compatible with all of that, and SpeechBrain is compatible. So any existing PyTorch code can be directly used in SpeechBrain as well. So then this kind of SpeechBrain then enters this whole ecosystem of things that exist, then all use PyTorch, and they can all be used together. Then there is also the Python ecosystem. So Python is the main programming language here, basically almost the only one, and Python is widely regarded as quite readable, which is important to us. Python is widely used in our field, so we want SpeechBrain users to actually write Python rather than use some kind of framework that was written in Python. This allows users to actually use the language that they like, Python, and also allows all of the kind of code to coexist together. So then all the code can access all, so for example, the recipe flow is defined in Python just like the model is defined in Python, so they can kind of cooperate if needed. Then Python also has a larger ecosystem of tools. This is also nice. So we can use pip to install SpeechBrain like we did just now. And there's, for example, PyTest for automated testing. And finally, SpeechBrain kind of leverages YAML as well. YAML is a human-readable data serialization language. So in SpeechBrain, we wanted a data serialization language for hyperparameter definition, and we, instead of like writing a full language from scratch, we wanted to base it on YAML, which is well known and also comes with some sort of pre-existing helpful tools like syntax highlighting. And I think it's these sorts of small decisions where the sort of grand SpeechBrain design principles actually show. So if we want a easy or well accessible toolkit that's sort of easy to use, then for example, having syntax highlighting for the hyperparameter files is important. Having Python as an easy language to write in is important, and that's kind of the level where it all gets implemented in the end, of course. Now, moving on in this tutorial section, I will kind of proceed top down. So we will look at a sort of an outline of an experiment and then focus on sort of the individual segments there. So let's go to the outline. So we have basically 3 files here to look at. The first one being the data prep script. So this is something that's specific to a single data set and can be shared across all tasks with that data set, basically. And the point is to just parse the dataset file hierarchy in whatever form the dataset is distributed in, and to create a dataset manifest file. So this would be a listing of each of the individual data points. So, for example, all the information that you need about each data point. So, for example, the path to the audio files and the transcript and the speaker identity or whatever you have for that dataset. So then I will not talk so much about the data prep script, since that's sort of more closely related to the to individual datasets, and it's sort of a necessary evil that's always needed in whatever. And SpeechBrain is not so directly concerned with these scripts. Only the sort of the manifest files are something that we will look at later. Hyperparams.yaml. So this is now the hyperparameter definition file, and it is or has kind of three different purposes, I would say, maybe. So first of all, you will have some basic experiment information. So it would be stuff like the seed for the experiment and some paths for the experiment, for example, where to put the output that's created. And then it will have some training and model hyperparameters. So this would be stuff like the number of epochs to train for, or some kind of model hyperparameter. For example, here I'm just calling it a gamma coefficient. But then the third one is something a little more active. So the hyperparameters file, when it is loaded, it will also construct the models for you, and not just the models, but also other objects that you need in your experiment. So that would be here, for example, you can actually create a instance of your custom class from custom model.py with this Python import path and pass it this gamma coefficient that we just defined earlier. So then the point being here that this will save a lot of space in the later when we get to the Python file. So you don't need to do a lot of import statements, and you don't need to do a lot of sort of initialization calls in the Python file, but rather you can sort of create a selection of objects that you need to work with in your experiment, and then just sort of in the Python side, you can just sort of connect those together and show how they are actually used, how they connect, right? And finally, in the hyperparams YAML, you can also organize. It may be important just for convenience to put, for example, all the PyTorch modules that you have in one place, since maybe all of the PyTorch modules need to be wrapped for distributed data parallel processing, for example. Now that's what the hyperparams.yaml file does. Then we go to the experiment.py file, and I've divided it further into three different sections here. This is also following the other tutorials I showed you before. So there is a subclass of brain. So brain is the central framework style object which defines this generic training loop. And what you need to provide in the subclass or override in the subclass are at least compute forward and compute objectives, which together define how the model is executed and trained. And then you can call brain.fit, which then runs this training loop, doing what you requested. So inside compute forward and compute objectives, you would do the connections that I talked about just now when I showed how things are instantiated in the YAML file. Then the experiment.py will also have some kind of data pipeline definition. Here it is, often it is a function that in the end constructs PyTorch datasets. So this would go from the level of sort of loading individual files of disk, doing some types of transformations on the incoming data, and finally the datasets which yield individual data points at a time. Then the third section of the experiment.py file, that would be the if name equals main block, which is this canonical Python script interface. And it defines the recipe's actual flow, so actual calls in the experiment. Let's look at sort of the different parts with some sort of boilerplate code. So we could have at the top some imports still. Maybe you need to import SpeechBrain at least, and then you will do the custom brain class definition, brain subclass definition, and then you will have the data pipeline, and finally the recipe flow, which could start with the command line running, then instantiate both the datasets and the brain subclass, and finally run the brain.fit and brain.evaluate methods, which do training and evaluation. So that's the outline that we'll look at. Now let's focus on the individual bits in them. So we're going a little bit deeper. This is as deep as we'll go, I guess. We're now at the code level finally. So hyperparameters. Hyperparameters.yaml. Now I'll just sort of call back to the outline of which file, which section we're talking about. Hyperparameters.yaml in this case. So the SpeechBrain team built this extended version of YAML, which we call HyperPyYAML, and I can here briefly compare it to normal YAML. So there's actually a lot of functionality in just normal YAML already that we are using. So in normal YAML, you can, for example, even instantiate objects when you load it, but the interface or the syntax is just a little bit clumsy in our opinion. So in HyperPyYAML we have shortened this bit to just !new, because this is the sort of thing that that you will write day in, day out. So sort of concise syntax is actually quite important in our opinion. In normal YAML, you can actually refer to things with anchors, but you need the anchors, like you need to actually write these sort of anchors, and then you can refer to them. Whereas with the HyperPyYAML version, we have decided to allow you to refer by key in YAML. So you can refer to base channels and it will sort of in the background insert an anchor here for you. The reference syntax also allows you to do some nice things like simple maths and quite crucially string concatenation. So if you have something like a data directory and a subdirectory in normal YAML, you cannot easily write this to, you cannot at all write this in some concise form, but with SpeechBrain you can actually refer to data directory and have it then sort of concatenate with /train. Let's play around with that a little bit. So I have here a string of HyperPyYAML. Normally, of course, this would be inside a file, but I want to sort of actively, quickly just change this. So then let's see what happens when I run it. So first, this string is loaded as HyperPyYAML. We get the hyperparameters out. We create this sort of 2-second bit of noise and transform it with hparams, whatever is referred to by the model key. And let's look at what the model key actually refers to. So, okay, it is a torch sequential consisting of a 1D convolution layer, then a leaky ReLU, another convolution layer, and another leaky ReLU. And when we run that, we can see that we get something of this shape. So it has 128 channels, the shape, the length is still the same because of the padding being computed out here. Let's change first just the base channels here. So you only need to change this, and note that the second layer's out channels was multiplied by 2, so we get 64 here. Then maybe something else. I can also demonstrate how this kind of instantiating the objects in YAML and then using them, connecting them in Python, decouples them in a sort of nice way where you can just use this, generate this h-parameter model, whatever the model is. It can be any kind of model. You will just call it with the audio. So let's say we want to change the model to only include the first layer. This kind of demonstrates that and how the decoupling works here. All right. Then we'll move on to data loading. So just a brief sort of reminder of PyTorch data loading. So since we're operating in the PyTorch ecosystem. And this is specifically map style data loading. So map style data loading is sort of random access data loading, which is suitable when you can do random access of some kind of fast hard drive. So typically this would be like a SSD on a compute node. Then you will have the most important object is a dataset, which loads a single data point at a time. The other things that are needed to form the full data pipeline are a collation function, which takes a list of data points and makes a batch, so that does batching. Then a sampler that determines in which order you iterate over the dataset. And finally, PyTorch has a data loader class which combines all the different things above and orchestrates the whole pipeline, and it can also load data in parallel into a buffer, so that's more efficient usually. I will soon also talk about briefly about possibility to do sort of sharded data loading. But first, let's look at this. So this is all to do with the map style data loading. This is random access data loading. You will need you will use in SpeechBrain these data manifests, and they are created by the dataprep.py out of the 3 files that we talked about in the outline. So the data manifest contains the static items of the data, if you will, static in the sense that they are unchanging, but also in the sense that they remain in memory once you load the data manifest. So SpeechBrain uses this kind of format where you have an utterance ID, and that maps to a dictionary of different keys. So it's all based on key access. So these all become sort of different static items. So you have the file path static item, the words in this case, which is the transcription static item. This utterance ID becomes the ID static item. You can use JSON, which is this format, a widely used format, or also CSV or anything that loads into dictionaries. So here I have an example of a sort of a toy example data prep script, if you will. So this in the end just dumps out this this nested dictionary as a JSON file. And then we can use, then we would go into the actual data prep function in experiment.py, and there we can load the JSON. One thing to note here, it's quite important for the data manifest file to be sort of relative to dataset root. Otherwise, you will have to, whenever you move the data, you will have to like recreate the data manifest files. And if it's relative, the nice thing is you can actually also share the data manifest files online if you want to. So then inside, now we are inside the experiment.py file and in the data prep pipeline. So this would be the second section of the outline of the experiment.py file that I showed you earlier. So now we're actually getting into the dynamic items as contrasted to the static items. So first, there is this generic dataset class in SpeechBrain called dynamic item dataset. And you can instantiate it from JSON. So I'm loading the JSON that we just dumped. And then I'm setting the output keys to ID and words and loading the first item. So we see that we can request certain items and by key, and the other items are not loaded. So this is managed by a dependency graph. Only the needed things get loaded. The output of the dataset is a dictionary. Then the dynamic items are things that are loaded dynamically, so they are not in memory the whole time. This would be things like the actual audio. So we are now sort of faking a signal for this presentation, but basically their dynamic items can take different static items by key and even other dynamic items by key and provide new items, so new keys in the dataset. So this takes the file path and the length and provides the signal item. Similarly, by dynamic item, you might do like on the fly tokenization for the transcript, or in this case, mapping the utterance IDs themselves, so the identities of the data points into integers. You will need to usually map labels into integers, and here also returned as tensors, as you'll want to work with tensors. So we add these different dynamic items to the dataset. And now we can set the output keys to audio ID and signal and load the first one. So here you see the value of not running. So the unload, the keys that we did not request. So if, for example, the tokenization was computationally heavy, then we would still save up on that since we didn't need it in this example. Then related to, or the next section in data loading will be batching. SpeechBrain has a class for this, padded batch, and this can actually be orchestrated by the brain class for you. So, so you don't usually need to use this class yourself, but it is used in the background automatically. But here in this example, we'll create a data loader with that collate function and look at the batch that first gets loaded. So first thing to note is that the padded batch class has this attribute style access. So this is the actual key that we requested. Those keys get added as attributes on the batch object. And this is one of those small things that I talked about earlier, which just make the code a little bit more readable, where instead of referring to something like batch element 0 you refer to it by name, by batch.signal. And then the second part is the signal is this sort of padded data. So it has the data itself, which has been padded. So that's an interesting and important part of variable length sequence processing, but which PyTorch natively does not handle. But SpeechBrain handles that for you. And besides the padded data, it has also these relative lengths. So relative because even though a lot of speech processing tools will sort of decimate the signal in some sense, somehow downsample the signal, the relative lengths of the signal of the different batch elements still stay the same. So those can be used for example, masking in later stages. So the way to access the actual data would be batch.signal.data. I will just briefly here mention that SpeechBrain also has dynamic batching, first for this map style dataset based on a dynamic batch sampler. And then I will mention, like I said, that you can also do sharded data loading. SpeechBrain extends the web dataset library for that. So that is sort of an ongoing project. Web dataset is being actively developed and might be included in PyTorch at some point in some form. So we're following that. And one thing that SpeechBrain, for example, extends web dataset with is on-the-fly dynamic batching. So that's important for particularly these variable length sequence processing tasks, which we have in speech usually. So sharded data loading is usable when, or you should use that when you are loading data of, for example, a network file system, some kind of shared file system. And finally, subclassing brain. So this is the class custom brain section. So here this would of course be a brain subclass like this. So in the minimal case, all you need to do is to override compute forward and compute objectives. But what do you actually put in there? How do you actually access the hyperparameters that you defined in the hyperparameters file? Well, so let's say we have these hyperparameters. So these new hyperparameters, we have this MFCC feature extractor. This model, it's just a linear layer in this case, this loss, this optimizer. So we'll load that that hyperparameter file, and we then pass the hyperparameters that we loaded to the brain when we initialize that. And then what we see is that they get added as attributes of brain. So again, we're using this attribute style access. So you can do brain.hparams.features, and that will access what you instantiated in the YAML. So then you get these feature vectors out. Similarly, the modules that we collected here, in this case just one PyTorch module, they get added as special brain.modules because they get wrapped automatically with different things, for example, relating to distributed data parallel loading, etc. You should access those via brain.modules. So, so when you're actually inside brain, inside compute forward, you can do things like you get the batch in, you run self.hparams.features and run it on the batch.signal.data. You get X. So in this simple, silly example, we're just picking the 5th element in the sequence, not actually doing any sequence processing. We're running just a softmax on that and returning that as the prediction. And then inside compute objectives, we're using the stage parameter. This automatically gets passed in by brain itself. So when in the training stage, we just want to return the loss, but in other stages, so this would be validation and testing, we just added a print here to have a look at the predictions. So this kind of also shows you how writing everything in Python is kind of nice for these sort of developing things, because you can just insert prints everywhere you need them, just to kind of verify that everything's going as you thought it should proceed. We will actually run the definition, and we get to the if name equals main block of the experiment, where we first instantiate that brain with the hyperparameters that we had loaded earlier, and then we call fit. So at first, with our 2 examples in our dataset, the training loss starts high, but quickly plunges down to almost 0. So what we're doing here is just based on the 5th element in the feature vector sequence, trying to determine which example it is out of the 2. And we will then evaluate again on the same data, on the training data, and now it prints like we showed. We put the print statement in there, and at least our silly example was able to completely overfit the training data and predict the correct classes. So that covers sort of the basic outline of how an experiment gets put together, what kind of different elements there are. Thank you.
All right. Thank you very much, Aku. And sorry again for the technical problems. What I suggest to do now is to go ahead with the example of a full recipe, and maybe later we can do the full Q&A session. So we are a little bit late due to these technical issues, but we can make it. So let me share my screen. All right. That is where we are. Okay. So we are here. We have seen in the architecture at least some insights on the general architecture. The original plan was to have 2 tutorials here, one on speaker identification and one on speech recognition. We are able to do only the speech recognition one because of the time limitation, but you can take a look at the speaker identification one online. So so we're gonna do this part. All right, so let me share my screen for what regard the tutorial. All right, so you should be able to see now. So if everything okay, you should be able to see the call-up tutorial we have for that. As I mentioned, we'll start from speech recognition. We are not able to do the one on speaker identification, which is a little bit simpler. But yeah, let's start with the speech recognition one. So first of all, before diving,
Mirko, we only see the slides for now.
Stop sharing. All right. Let me share my screen again. Good. Voila. Do you see the tutorial now?
I don't know for Aku, but maybe it's a bug on my side. I still see the slides.
Yeah, same.
on my side, it looks like I'm sharing the. Okay, so let's do that. Let me try to share again. Oh my God, this platform. Let me share again the screen. So the entire screen. All right. So do you see my screen now?
No, but it looks a bit frozen, right? So I don't know if you don't have to like.
But do we have the same issues as before?
I think we. No, I don't know. Maybe you have to reconnect, right? Like to.
Okay, just 1 second. I don't know. So I changed the screen, right? So stop sharing. Yeah. So let me share my screen again and hope it will be fine. Do you see it?
Yes, looks
All
like.
right. Finally,
Yeah.
many things are not working. But anyway, okay. So in this tutorial, we are going to present kind of. We are going to tell you how to implement an state-of-the-art speech recognition from scratch with SpeechBrain. So let me give you an overview about what is the pipeline involved in a typical speech recognition. This is the pipeline that we are going to implement. So we start from the raw signal. We can perform optionally on-the-fly data augmentation from the raw signal. Here we can use time dropout, frequency dropout, speed change, noise, reverberation. Then still on the fly, we compute feature extraction. There are many options here. For speech recognition, typically we use filter banks. After feature extraction, you have the speech recognizer. Here we support different technologies, we'll see later. And on the top of the speech recognizer, you can have beam search coupled optionally with some language model. So here we support different beam search techniques. The first simple one is actually greedy search. We have beam search plus language model, and also beam search plus CDC plus language model. So the beam search here is implemented in a batch way and on a GPU. For what regards speech recognition, we have many options, popular options. The simplest one is to have an encoder followed by CDC. So that's something we can have. Another option is transducer. We have our own implementation of transducers where we may have an encoder, joiner, and predictor. And also we implement encoder-decoder architectures with attention mechanism connecting encoder and decoder states. So here we can have like recurrent-based models or transformer-based models. And what we are going to do today is to implement this kind of pipeline, encoder, decoder, and actually more complex because we are doing multitask learning, because on the top of the encoder, we are going to add a linear transformation and a CTC loss. So we are going to implement kind of multitask system where we have encoder, decoder, plus attention, plus CTC. So that's the system normally giving the best performance and actually use a lot also on other toolkits like, for instance, ESPNet. Okay, so yeah, this on top of the speech recognizer, we have the beam search. And yeah, step number 0, what you have to do is to just install SpeechBrain. So you just click here, and in a few minutes, you are able to install. Specifically, I didn't want initially to start from the speech recognizer because the speech recognizer is a little bit more challenging and requires multiple steps. But yeah, to implement a speech recognizer, you have to, first of all, prepare your data. Step number 2, train a tokenizer. Step number 3, optional, train a language model. You can do it only if you have kind of an external text corpus for that. And step number 4, train the speech recognizer itself. Here you are just to go in the right folder where you have the training script and write Python train.py train.yaml. Once the training is done, you can train. You can perform inference on top of your train model, as we have seen previously. Step number 1, prepare your data. So, as mentioned in SpeechBrain, we use data manifest files, which are in CSV or, like in this case, JSON format. What you have to provide for speech recognition is this information. So we have kind of a unique identifier that identifies the sentence, and then we have some kind of fields. Waveform is the field with the path of the waveform. Length is the length of the sentence in seconds. Is only needed if you would like to sort sentences before batch creation. And finally, words. This is all you need, right, for speech recognition. We have the waveform, right, the path of the waveform, and the sequence of words. That's all we need for end-to-end speech recognition. So one remark here, as mentioned before, here the data preparation in general is dataset dependent and task dependent. So we already prepare data preparation for the most popular data sets, but you can, if you have your own custom data set, you may want to create a kind of preparation scripts that in the end outputs these files. Another remark here is, here we are using some kind of entries, some kind of fields here. We are not forcing users to any specific name here. So you can have, instead of wave, you can have file path, or instead of words, you can have something else. The only things that we require to the user is to be consistent, as we will see later, with the train.py file. So here, I think it's a pretty flexible way to prepare data. Users can define the fields they want. We just ask to be consistent later on in the script. Tokenizer. Tokenizer is a very important component of a speech recognizer, which defines actually the output targets. As for output targets, we have different options. One option could be to use characters as tokens. Like in this case, you can do the city of Montreal, you can convert in the corresponding sequence of characters. That's a good choice, but has also some disadvantages. Characters, are good because we have a small number of characters to predict, and thus we have probably we have enough training materials for training characters. Another good thing is that we may have better out-of-vocabulary generalization. The bad thing is that we have to, estimate long sequences, which from the machine learning point of view is not an ideal. Another idea will be to use phonemes as targets. Phonemes will be the most natural way to do speech recognition, but the conversion between words and the corresponding phonemes might not be trivial in some languages, and typically with end-to-end speech recognition, we prefer to not doing it. Another possibility will be words, yes, here also there is a trivial mapping between. You can say like the city of Montreal, the city of Montreal. This is not really a good choice because it's kind of the good thing is that the output that you predict will be short, but you cannot really play well with out-of-vocabulary words, and there might be some tokens for which you don't see enough training materials. So the good thing here is that there is some kind of compromise between characters and words, and this compromise is the tokenizer. So there are different ways to tokenize your input training data, training text. So you can, the way we're using SpeechBrain is byte per words encoding, and we rely on the sentence piece tokenizer. So in this case, this idea is to allocate full tokens, full words for popular full words for popular words, and subword tokens for words which are less popular. So like here, you can write the city of Montreal could be like the city of Montreal. That's a good compromise, and we use it in SpeechBrain as well. So here, to train a tokenizer, let me go quick here because I would like to focus more on the ESR part. But it's always the same story. You have to go in the right folder and train the tokenizer. You have train.py, train.yaml. Here we are not doing too much. We are just calling a sentence piece tokenizer on top of the training transcriptions, because we have to train the tokenizer on top of the training transcriptions. So in the end, right, what we do here, right, after training the tokenizer, you can use it. This is the model that we train, and then you can use it. And in this way, the city of Montreal is tokenized like the city of Montreal. If you call the encode as IDs methods, you already have the sequence of IDs. So you have the sequence. So with sentence piece, you convert every token to an integer, and this is the sequence of integer that we use for training the model. The other optional step will be to train a language model. Normally, you have to train a language model on huge text data. Here we are going to train the language model only on top of the training transcriptions, which is not the ideal condition, but at least we can show you some example. So this is optional. These days, we are seeing very good performance even without training, coupling the speech recognizer with an external language model. Think about this is especially true when we use self-supervised learning and techniques like that. But still, in some cases, the language model might help. So you can train it with SpeechBrain. Again, here, you have to go in the right folder, train.py, and the hyperparameter file. So yeah, actually, and if you would like to change device here, you can do device CPU. And if you have the GPU, which is not the case in this collab session, you can do code 0 or whatever you want. While training, you can see that, you can see this log, you can see the training loss, the validation loss, and so on. So this is a kind of dummy task because we are training on top of transcriptions. And yeah, I didn't mention before, but here we are using a mini LibreSpeech just to have something quite quick to show you. But in the real case, you have much bigger data set. So once you have trained the language model, you can train the speech recognizer. So let me go here. So here I actually training it on the CPU, so it's gonna take forever. Yeah, again here, I would like to stay more on that part. Here you have to go in the right folder, in this case this one. You have the training script, the YAML file, and then if you want, you can override from the command line some of the parameters that you define in train.yaml. But let's take a closer look at how the YAML file and train.py files are in a real case. So let me switch here to the code directly. I hope you are going to see it. So we are here, SpeechBrain template, speech recognition, ASR, and let's take a look at the hyperparameter file. So yeah, at the beginning, you have to set up a seed, like for instance, seed is necessary for the random initialization. Then you have to set up some folders, like the folders where you have the data. In this case, we are automatically downloading the data from the web because this is mini LibreSpeech. You have to set up the folders where you would like to save your output, the word error rate file, the checkpoints, and the logger. So you just declare some folders that you are going to use. Then here, we will see later, here we define also the place where we would like to store the data manifest files that are created in the data preparation step. Here, then we can define some parameters that we are going to use, like we can define a bunch of training parameters, like number of epochs, a number of epochs where CTC is active. So as I mentioned here, we are doing multitask learning, the batch size, the learning rate, the weight to give to the CTC loss, etc. Then there are also other parameters for feature extraction. Here we're using MELs, 40 filter banks, and we are using a CR-DNN model. And here are the parameters of our encoder, and here are the parameters of the decoder. So here, for instance, for the decoding, for the beam search part, actually parameters important are the beam size, the language model weight, etc. So one important thing, so here you see we define some parameters, but we also define the object using these parameters. For instance, I don't know, we said number of MELs. Who is using number of MELs? This is used by the compute features. Who is using, I don't know, let me go here, test beam size. This is used by the beam search object. Who is using, I don't know, let me see, RNN layers. RNN layers are used by the encoder. So here, you're not defining the parameters in a kind of plain way, but you also always have a visible connection with the objects that you define jointly within the hyperparameter file. So, and then that's the same for others like learning rate. Let's see who is using the learning rate. Learning rate is used by, maybe not, let me see if, learning rate, yeah. So it's used by the optimizer and by the learning annealing object. So yeah, here we can define a bunch of parameters, and then we have to define the objects using the hyperparameters. So, and here we just itemize them, right? So we define an object for feature computation. Here we use filter banks. We define an object for normalizing these features. Here we do mean and standard deviation. Then we define objects for the environmental corruption and data augmentation. Here is an object that automatically adds noise and reverberation to your input signals. And here is another object for data augmentation that can do many things, including like speed change in your input. Then we can define our encoder. As I mentioned here, we are using convolution, a model called CR-DNN, which uses convolution, recurrent layers, and finally DNN layers. And here are all the parameters of this model. We have a decoder, right? In this case, we are using a simple attention-based decoder that based on a simple GRU. And then we have other modules like this CTC linear transformation on top of the encoder, and a linear transformation, sequence to sequence, on top of the decoder. We can define many objects here, a tokenizer, for instance. We have to put all the objects in these special variable modules to make sure the brain classes, it will put them on the right device, like CPU or GPU, or on the right modality, like training and eval. So all models that have parameters typically should be recalled here. Then we have other models here, like we define a language model, the beam search objects, and the system in the learning rate annealing objects, the optimizer, the checkpointers, etc. So that's pretty much it. Actually, here we also have another object because here we would like to, we have declared language model, tokenizer, etc., and we would like to pre-train with existing checkpoints, and that's the way we do. So this is the pre-training. The pre-trainer here is used to link the language model with a corresponding checkpoint, the tokenizer with a corresponding checkpoints, and also if you would like to pre-train the model, not starting from scratch, you can add here a checkpoint. So here we define the object and functionalities, and the train.py, we use them. So let's see what we do here. So in train.py, we have this call main. The first here here is the starting of the script, the pipeline. We read the command line. Here is a call that is needed to support multiple GPUs if you would like to use multiple GPUs. Here we read the hyperparameter file. So at the end here, you're going to have a dictionary with all the objects defined in the hyperparameter file initialized. We create a folder. We prepare the data. Data preparation here is the step that creates the JSON file, the data manifest file that we have seen before. Then we have here this call, data.io prepare, that takes in input the hyperparameters and gives you in output the data sets. You can go quickly through here. Basically, here is where we show the data.io pipeline. You remember at the beginning I show you that you have this file called wave, this field in the JSON file called wave that contains the path of the signal to read. And here we are processing it, and basically in a simple way where we read the path, we read the audio, and we return a tensor corresponding to this input signal. It's here where you have to be consistent with the JSON file. So remember, in the JSON file you add wave, and here you have to define how to process this entry. We can do the same for the other entries. You remember in the JSON file there was the entry words, and here we process it. Actually, here what we are going to do here is to use the tokenizer to process the word sequence and encode them. And then we also output other useful things like the tokens with the beginning of sentence appended, the tokens with end of sentence appended that will be useful later. But yeah, you define here the pipeline, and then you can call this function from our dynamic item datasets that, given the JSON file and the data transformation pipeline, creates your datasets. So once we have created our dataset, everything is ready. We can initialize the brain class. The brain class is the core class for doing a train loop. Once we have initialized it, we can call the fit method, which is actually the method doing the training loop. And after the training loop, we can perform evaluation. So let me just show you here how is the brain class for this specific example. So here, as you can see, right, we expose directly the forward computation. So in the forward step, what we are doing here, we basically compute the features. So we have a sub function here for doing that. So you can see here that when we are in training modality, we perform data augmentation. Otherwise not. We compute the features and normalize them. Note that here are actually the same object that we have defined in the hyperparameter file. So feature extraction. Then the other important thing here is the encoding part. So we apply the encoder, and then we apply the decoder. And that's it. Actually, the decoder is autoregressive. So you have to, in training, right, you have to feed the previous token. Actually, also during tests, but in training we have the previous embeddings. In tests we are doing something different. So here you can see that when we are so here when the CTC is active, like we perform prediction of the CTC. If we are in validation stage, we run the validation search. When we are in tests, in test, we run the test search with the beam search. Then the other important method is the compute objective. The compute objective tells you how to switch, how to pass from the prediction and the targets to the corresponding loss. And essentially here, we are just computing the non-negative likely loss on top of the predictions and on top of the targets. As mentioned here, we also have multitask learning with CTC, and here is where we combine this negative log likelihood loss with the CTC loss, according to the weights that we specified in the hyperparameter. That's pretty much all. There are many other smaller things that you may want to familiarize, like for instance, when we end one stage, there are a bunch of things that we do, like collecting some metrics. When we end the validation stage, we can do learning rate annealing. We update the optimizer with the new learning rates, and we save the checkpoints. But that's pretty much what you do. So this is a pretty elaborated recipes because there are many components, but on average, everything is even simpler. So if you take a look at speaker ID recipes, speech announcement, they all share the same structure. Even though the tasks are different. So what is different is, the way you perform the compute forward, the way you compute the objective, but all the recipes for all the tasks, they share exactly the same structure. All right. That's all for me. I'm very happy to leave Titouan for the conclusion, and then we can start the Q&A session. Thank you very much for your attention, and Titouan, feel free to go ahead with your part.
Sure. As soon as I get the right to share my screen, I'll do it. Okay, I got it now. Okay. So hopefully you should be able to see it now. Mirko, can you confirm that it's showing?
Yeah.
Cool, great. So apologize again, everyone, for the different difficulties that we encountered and the fact that we are a bit late because of that. But these are the two last parts, and then they will be pretty quick because they concern where we are going, what are the next steps, and how you can contribute to the toolkit. So the very first question here is, what is a roadmap, right? Like, why do you want a roadmap as a toolkit? So the question here that really needs to be answered is, what's the purpose of having and defining a roadmap? The thing is, with your toolkit, right, the first thing we would like to do is to be transparent. So we would like to expose to the whole community, because in the end, we are not building all this just to use this for our own research. I guess this is pretty clear now, but it's so everyone can use it. So we have to be very transparent on where we want to go, where we want to put resources and effort to develop specific tasks or specific features, etc. And so being transparent is super important here, because if you are not transparent, then you just can't involve the community, right? And we want to involve the community. We want we want everyone to be interested in SpeechBrain and say, hey, you are missing this part, and me and my team, we are interested in doing it. So we would like to get some help from you guys to better understand how we could implement this in SpeechBrain, right? So we have to be transparent, explain what we want to do, so people can come and say, okay, you want to do this, but we want to do this instead, and we think it is important to do it. So we can add this to the plan, right? Like the SpeechBrain plans. And of course, if we combine all of this, then we want to be ambitious, right? We don't want to just look at the current state of the art and say, we need this, we need this, we need this, right? Like, what we want is to have something more. We want to do research with the toolkit. So if we are not transparent and not involving the community, in the end, of course, you cannot be ambitious, because you will always stay on your own research or just the things that exist. and implementing things that exist that is not interesting. To fulfill all these goals, right, we decided to go with this course. So, well, basically, if you go over this link here, you will it's just a discourse that I showed earlier, right? So you'll just find the plain list of the different things that we would like to do, right? So I think it is open here, right? Community roadmap. And so you have a full list of all the different things we would like to do, topic after topic. So we won't discuss them here, mainly just the shortest ones later, but you have the full list, okay? And the good thing is, like, if you're interested to add any other topic to this, just open a discussion on Discourse, and if any interested peoples will join you, then we will just add it to the roadmap and say, this is a new next goal for SpeechBrain. This is how you involve the community, right? Discuss about what needs to be done next. Okay, so for the long term, again, refer to the Discourse, because we have many ongoing things that we would like to aim for, like more multitask or combined pipeline, complex pipeline, like having speech enhancement plus maybe, I don't know, or just doing VAD, voice activity detection, into speech enhancement, into speech recognition, into maybe spoken language understanding, on top of that. I mean, having complex pipeline. We can do it. We already did it for some receipts, and these are things that we aim to develop. But of course, there are many others long-term objectives. The most important ones, I guess, are the ones that are at short-term, right? Because they are going to be merged very soon, in less than 2 months, probably. So the first one is CalD2 integration, since we are collaborating with this team, and it seems to work pretty well already, and we should be done soon, hopefully. Then we have 2 refactoring concerning the decoder pipeline and transformers. So when I say refactoring, don't think it's like, oh, it was not working properly beforehand, so they had to refactor it. This is not the point here. The point of refactoring in SpeechBrain, when we do refactor something, it means that we want to be even more transparent. We were not satisfied with the way it was implemented before, and the fact that some part may still look a bit, black box for the users. And this is definitely something we don't like with SpeechBrain, so this is why we are refactoring it. And now you will be able to decouple everything and just build your own custom decoder pipeline if you have, I don't know, different scorers, for instance, or different decoders, or if it's in the case of transformers, you would like to have a CRDNN encoder, some specific layers in the middle, and then plug a transformer decoder on top of that. You will be able to do it very easily. Then we have text-to-speech coming on. We already have models implemented. They are just under review, and we just have to train them on bigger data set now, like Tekotron. We have like the WaveNet vocoder that is also being trained. And we have another very big piece coming on, which is self-supervised training with Wave 2, Wave 2.0, Pace Plus, or others. Here, I would like to emphasize on the training, right? It's not just using them. You can already use them within SpeechBrain. So if you have a pre-trained Wave 2, Wave 2 model, you can plug in and do whatever you want. Like we already have received for speech recognition, for instance, but you could do spoken language understanding or other speaker ID, whatever. You can already use pre-trained self-supervised learning models. Here, we would like to train them from scratch now. And this is quite long to do because the original implementation is sometimes quite hard to get, and then it takes some time to replicate the results, of course, because these are very, very big models, and so, well, it takes time. And finally, as well, voice activity detection, which is an important component, but also very hard actually to achieve, because there is no real solution that works always well. And the problem is like voice VAD is a very important block when you want to, put in production some certain model, because you need to segment your audio files when people are talking. And so this is a crucial point that is hard to do. And this is why we are still working on that currently. Right, so that's it for the roadmap. Then the question becomes, how do I contribute to SpeechBrain, right? This is a community toolkit, so we need you to contribute. So the first thing, of course, is just to use it. Like, use it, report bugs, find issues, report them on GitHub. We will answer as quickly as possible. Try to maybe even propose new changes on the code or whatever if you think that something doesn't work properly. But if you want to contribute like with your own code, right? Like actually contributing to the code, then you have to follow a certain number of steps that are actually 5. The very first one is to find a task of interest in the roadmap or come with your own. It's better if you look at something in the roadmap. If you have some spare time to code, for instance, look at the roadmap and say, hey, I would like to do this. Notify us so we can help you, and then select this. Or just come with your own, right? Like if you want to implement a recipe for a specific data set or a new task, or just do it, right? Do it. The second step is to open a pull request on GitHub. This is very important, even if like you are not done with your code, because if you don't do this, we can't really help you. As soon as you start a pull request, we can jump into the code and look with you if you have any, problems. You can directly engage with the SpeechBrain team, so we can maybe even touch the core of SpeechBrain if something is really needed. The third step is that once you are ready, once your code is completely ready, we will assign you fixed reviewers, and so they will look at your code, right? So everything we discussed since the beginning of this tutorial about documentation, about the way of being compliant with a certain norm, etc. We will look at all this. It's just like going through the review process of a paper. Instead, here we will most likely reply very quickly to every single rebuttal that you could come up with. But the thing is, you will have to comply to the SpeechBrain standards, and this is crucial for us to scale, right? If we don't do this, we might end up with something that in 1 year might be completely noisy and we won't understand anything. So this is quite important. And of course, you do the request change. If you don't, it won't be merged. That's as simple as that. If you don't change the thing, we cannot merge your work to SpeechBrain. And well, once you did everything, we simply merge this into the develop branch, so it won't be in the latest stable version up until we emit a new version, a new stable version of SpeechBrain, so we can, let some time to test the functionality to see if people's remark problems when using it, etc. And that's it. That's the way of contributing to SpeechBrain. So it's, many people's already went through all the steps and everything went fine. We already have merged functionalities coming from people that we never heard of before, for instance, and that's great. This is what we want to see, because we actually need you to make this toolkit work on the long term. So as Mirko said earlier, we have this call for sponsor opened, and very quickly, you can just see the list of people that are joining us on this second round already. So we have Hugging Face, Naval Labs Europe, and Via Dialogue. And if you're, looking for not only sponsoring SpeechBrain or whatever, just interested in seeing if we have jobs opening or whatever, do not hesitate to contact us directly, and we are happy to answer you if it's the case, or follow SpeechBrain, of course, on the social medias, where we will advertise any opening we have. Again, we are sorry for the problems we faced during this presentation. I hope that everything still went fine for most of you. So thank you very much for your attention. And I guess now we can hopefully take some time for questions if we have some.